Kepler's law of planetary motion. Objective: to understand the Kepler's laws of planetary motion. The earliest known theory of planetary motion was Ptolemy's geocentric theory of planetary motion in the 2nd century, which suggested that the Earth was stationary at the center of the universe and the stars and the planets, including the Sun, revolved around it. Nicolaus Copernicus in the 16th century theorized that the Sun is fixed at the center of the universe and all the planets moved around it in perfect circles. His theory was known as the heliocentric theory of planetary motion. Tycho Brahe had researched the motion of planets for over 20 years, but did not live long enough to analyze the data he had collected. Kepler consolidated Tycho's data to put forth his 3 laws of planetary motion. Kepler's first law, the law of orbits. Contrary to the popular belief, planets do not revolve in circular orbits around the Sun. Kepler's first law states that all planets move around the Sun in elliptical orbits with the Sun at one of the foci. Kepler's second law, the law of areas. Kepler's second law states that the line joining the Sun and planet sweeps out equal areas in equal intervals of time. For example, the area swept by the Earth in March and April equals the area in May and June. For an elliptic path, the orbital radius and angular velocity of a planet around the Sun vary. Suppose a planet that is at a distance r from the Sun covers an angle d theta in time dt. Area covered by the planet dA is equal to the area of a triangle with sides r and r, angle between them being d theta. Area of this triangle is half r square sine d theta. Since d theta is small, we can replace sine d theta with theta. Rate of area swept by the line dA by dt is equal to half r square d theta by dt, which is equal to half r square omega. Torque of the planet about Sun is 0, as the gravitational force on the planet acts towards the Sun. Hence, angular momentum of the planet L should be constant. L is equal to mr square omega. R square omega equals to L by m. Substitute this in the expression for dA by dt. dA by dt is equal to L by 2m, which comes out to be constant. Hence, the planet sweeps equal areas in equal intervals of time. Kepler's third law, the law of periods. Kepler's third law is concerned with the time period of revolution of the planets. It states that the square of the time period of revolution of a planet in its orbit is directly proportional to the cube of the semi-major axis of the elliptical path around the Sun. For example, for Mercury, the length of the semi-major axis is 0.39 astronomical units, and its time period around the Sun is 0.24 Earth years. For Mars, the length of semi-major axis is 1.524 astronomical units, and the time period of revolution around the Sun is 1.88 Earth years. Observe that the ratio of the square of the time period to the cube of the semi-major axis is almost the same for both the planets. Summary: Kepler's first law states that all planets move around the Sun in elliptical orbits, with the Sun at one of the foci, not at the center of the orbit. Kepler's second law states that the line joining the Sun and planet sweeps out equal areas in equal intervals of time. Kepler's third law states that the time period of revolution of a planet in its orbit is directly proportional to the cube of the semi-major axis of the elliptical path around the Sun.